we talked specifically about the neuron. And we're not going to be really talking about the neuroglia anymore. We know that they are the supporting cast, which we talked about. And we spent a little of a chunk going over the different types of neuroglia. But what we really want to hone in our focus is specifically on the neuron. Because we have to understand that the function of the neuron is to send communication through the cell and out to the next target. And that next target is the effector, whether it's a muscle, whether it's a gland, or another neuron. Okay? And what we talked about on Tuesday was the generation. We first talked about the resting membrane potential. We talked about the contributing factors as to why it's negative on the inside of the cell. And the essence of what we're trying to get at is we're trying to create electrical changes in the neuron. They're very sensitive. We're creating electrical changes that would be able to propagate down the axon of the neuron. And you're basically you're gonna have a fuse that's literally lit, and it's gonna flow all the way down. And by the time it makes its way down to the axon terminal, we're going to be able to see the chemical portion of the communication that happens between the neuron and the effector cell. So where we're really talking about right now, when we talked about graded potentials, remember, graded potentials were driven by, our graded potentials were driven by the ions moving into the cells. So where we were first talking about our first gated channels were located on the dendrites. And we talked about things that would cause depolarization. And you guys already answered that question, that this would be sodium. Sodium going into the cell would make it a little bit more positive on the inside. What we talk about that's taking place here, we'll talk about the end of today. The same channels that are over here. The mechanism that causes these channels to open that will cause a depolarization or a hyperpolarization also takes place over here. So these, essentially, when we're looking at it, these are neurons just talking to each other. And in order for that to take place, we need to see some electrical conduct that takes place that moves this signal to take place in the axon terminal. So going back to where we left off, let's take a look at a quick review so we can sort of tie this in for you. We'll take a look at we'll touch a little bit on the resting membrane potentials, and we'll look at graded potentials. And from this is what we saw. We saw, when we first started off in our cellular lecture, I had you guys look at the intracellular differences, the intracellular and extracellular differences in the ion concentrations. And the two that I had you cover, sodium and potassium. And then what we're going to be looking at next, at the end of today, is looking specifically at calcium. Chloride, you'll see also chloride channels are also involved. And we don't really spend too much time on this, but if you can just appreciate what the two ions that we're going to be looking at when we first talk about today, and when we look at the dendrites and look at specifically the cell body, the exchange that's going to be taking place, the movement of ions are primarily sodium and potassium. And what we first have to establish is looking at those concentrations. And you don't have to memorize the concentrations of these, but what you can see, for sodium, you can see that's 137 millimolars of sodium on the outside of the cell and 15 millimolars of sodium on the inside of the cell. So looking at this, you can tell what the concentration gradient is. Intracellular, at least the direction is intracellular for sodium. There's a drive for sodium to move from a high concentration down to a low concentration. Now looking at potassium, you can see that that's the reverse. Potassium is high on the inside. We have 140 millimolars on the inside, 5 millimolars on the outside. And that describes the concentration gradient that I'm going to have you guys fill out over here. So here you can see the gradient, the direction of travel for sodium would be in. And for potassium, what would be the concentration gradient direction? Going out. This would be out. Now that we've looked at the concentration gradient, which is described in red, now what we can look at is the electrical gradient. By those three virtues that we talked about that lead to the intracellular, negative intracellular environment, And that's our leaky potassium channels. Those are the anions on the inside, and our sodium potassium pump pumping out more cations than pumping more cations out than in, makes it more electrically negative on the inside of the cell. Now, if I'm going to take a look at the electrical charge of these ions, it's negative on the inside. Now I've got a cation on the outside. Which direction is the electrical gradient? I have a positive ion and a negative on the inside. Which way would that cation move? Into the cell, right? Positive would be attracted to the inside. So if I were to open up these channels, by virtue of a positive ion wanting to move inside. So the gradient for that, the voltage gradient, would be in. And lastly, if we were to take a look at our potassium, we have a cation that's on the inside of the cell. It's negative on the inside, positive on the outside. What is the direction of the voltage gradient? Is it out? No, it's, I've got a positive ion inside, and it's negative on the inside. If I imagine that positive ion moving out down its chemical gradient, there's going to be a little bit of a pull because there's a positive ion wanting to be attracted to the inside. So therefore, the electrical gradient is into the cell. So that explains our gradients there. And if we were to take a look at, based on all the cells at rest, the only thing really active at rest are the leaky potassium channels. None of the other voltage-gated channels that we'll be talking about, that we talked about on Tuesday, and the ones that we'll be talking about today, at rest, the only ones that are, the only ions that are moving are potassium ions moving out. Okay. And as those potassium ions move out, we can see that the permeability is higher for potassium than it is for sodium. So therefore, we would see that the equilibrium point for potassium, and that was the example that I talked about, where if I were to turn on only the potassium channels, we would see that the equilibrium point would be about negative 90 millivolts. And then that was the other example where I said, okay, now I'm going to turn off the potassium channels, and I'm going to turn on only the sodium channels. Sodium would want to rush into the cell, and when it equilibrates, it would be around positive 55. And that's because sodium wants to drive through its electrical gradient as well as its chemical gradient. And then at rest, it would be positive 55. So the direction of where we are at rest, because of its primarily the potassium movement, brings itself closer to negative 90. In fact, the resting memory potential is negative 70. So now let's take a look at the sodium-potassium pump. And one of the things I was thinking of putting was one of the quiz questions today is, what is the entire role of the sodium-potassium pump? Because I know from the last quiz, you guys mentioned that ion movement, some of you guys put the answer for ion movement being active, if it moves from a high gradient to a low gradient, and that's not true. Ions just move down their gradients, and it doesn't cost any energy as long as channels are there. But what does require energy is the movement of those ions back to the side where they belong. So in order to drive sodium back out, if sodium makes it in, we got to drive it back out against its concentration gradient. Same with potassium. The potassium that made it out through the leaky potassium channels need to get driven back in. Okay? And so that requires energy. Anytime we're pumping against the gradient, we have to look at the mechanisms of how the sodium-potassium pump works. And so when you look at what's taking place, we're trying to drive sodium out into the extracellular fluid, and we're trying to drive potassium back in. And so we get our sodium ions. We get three sodium ions that bind to this pump right here. Okay? And once those 3 sodium ions bind, you'll see that will stimulate the ATP to come phosphorylate that entire pump. And what that's going to do is going to cause a conformational change in this pump that opens up onto the extracellular side and forces those sodium ions out. Okay? So that phosphorylation is the activation of this pump. And now you'll see that now that sodium's out, you'll see that phosphate ion still attached. And you'll note that the change of the active site for sodium changes so that it squeezes out those sodium ions. But take a look at those potassium active sites. Those change as well. So now this is going to allow potassium to bind in. And once potassium binds in, that's going to eject that phosphate ion. So now we're going to have ADP, and phosphate ion kind of just resting there. And they're going to get phosphorylated all through the process of cellular respiration. Once that last potassium binds in, again, that's going to cause a conformational change back so that it opens up intracellular to dump those two potassium ions back in. So the net effect is we have 3 cation ions out, 2 cation ions in, leading to a more negative on the inside. And the entire premise of the sodium-potassium pump is really just to restore those concentrations back. So think about that today as we go through the ion changes that happens in this neuron. These things are always working. Now, when we talked about the graded potential, we talked about the changes in that negative resting membrane potential. And that all involved the movement of ions. And if we were to take a look at the top right, here you can see the membrane potential. We're starting off at -70. And off at -70, you'll see that any movement of ions, and the specific ion that we talked about that causes a depolarization, these were positive ions moving into the cell. And what was that? That was sodium moving into the cell. Would decrease the membrane potential difference. In fact, it would bring it from -70 and it raise it up a little bit depending on how much sodium moved in. So if you had 1 sodium move in, that would cause a little blip, a little bit of a depolarization. And then the sodium-potassium pumps are sitting there pushing that stuff back out. You're taking that sodium that made in, pump it right back out, and you're going to get back to your resting membrane potential. So depolarization would be the upswing, and then the repolarization is bringing it right back. That's restoring it back to resting membrane potential. That was our graded potential. And so if I were to take a look at sodium coming in, and I get a little bit of a rush of sodium coming in, what the graph below on the bottom left is showing you is that if it's already negative on the inside, and I've got sodium coming in, that's going to cause a bit of a depolarization, where now you're going to get the polarity starting to decrease a little bit. And if I were to measure at this point right here, where I'm starting to see an increase in the sodium concentrations, I would probably measure it at this point would be about -60 millivolts. Or even closer to -55 millivolts. But if I were to measure the differences in that membrane potential further away, it would start to decrease. Okay, let me give you a better example. If I were to take a spoon, right, take any metal object, and I were to take a lighter, and I'm going to light it right in the middle, do you think it's only hot right at that point where I'm putting the flame?
No.
No. If I were to touch close to that point of the flame, yeah, I'd probably burn myself, and it would be really hot. But if I were to even take a couple finger lengths away, it would still be hot, but not as hot as that initial contact point. So that's exactly what we see when we see sodium coming in. So think about sodium as it comes into the cell. You get a little sodium coming in, you're going to have the highest concentration over here, and over here where sodium is still around, the concentration is less, but that's still going to represent a difference in the membrane potential. So there's a loss of charge the further we get away. Now, looking at this also, sodium is also moving in. So I've got this wave of sodium coming in through those ligand-gated channels. You're going to create this wave of sodium coming in. It's like if I were to throw a rock into a pond, you would see these waves taking place. And if I were to measure the sodium concentration here, it would probably be higher. If I were to measure it over here, maybe a little bit less. Over here, a little less, and over here, a little bit less. So the further away from that site, I'm going to see that sodium concentrations are going to decrease a little bit. And again, so that is going to be important when we start talking about sodium moving in, because the area, as the changes of the electrical voltage difference changes, we're going to want to start to get depolarization into the specific area that is most sensitive to voltage changes. And that area is the axon hillock. And I'll talk about that in our next couple slides. So this is where we saw depolarization. And depending on which ion is moving out, whatever neurotransmitter binds to, there could be a potassium channel here that is also ligand operated. There's even chloride channels that are ligand operated. And so if I were to look at potassium channel, if a neurotransmitter bound to this, which would cause potassium to leave the cell, that could cause a hyperpolarization, right? I got a positive ion in an already negative cell. I've got a positive ion moving out. Isn't that going to make it more negative? That's a whole premise of hyperpolarization. And if you were to take a look at hyperpolarization, it's a little bit downward, and so forth. So all of these are graded potentials that are taking place specifically in the dendrites or the cell body. Now, as those graded potentials move, right? Now we're going to take a look at the changes that are taking place, and that electrical voltage difference changes takes place along the cell membrane. And eventually they're going to make their way. You got these waves of sodium. We're just going to talk about sodium for now. Sodium's going to move down the waves. It's going to make its way over to specifically the axon hillock, where we see the most voltage-gated sodium channels. And these were the channels that we talked about. We talked about leaky potassium channels. We talked about a little bit about our ligand-gated channels. Now we're talking about the voltage-gated sodium channels. And so here what this image is just showing you is that close to the point of stimulus, you can see that this is going to create the highest depolarization. And if I'm making my way down to, and here you can see the shape, and all this right here that I'm drawing, this entire circle is the cell body. Right here is the axon. And this entire area is the trigger zone that I want to point out. This is the area, I'm talking about the changes in electrical voltage that propagate all along that cell body membrane up to this point. Because if the changes in membrane potential take place all the way out to here, if I can activate these sodium channels, that's going to cause a bunch of sodium to move in. So I'll get to that piece in just a little bit. Let's talk a little bit about those voltage-gated channels. We have our two that we have on here. Our sodium voltage-gated and our potassium voltage-gated. And the key thing that you need to understand about the difference between these two, not only do they move different ions, but by the design of the potassium voltage-gated channels, they're much slower than our sodium voltage-gated channels. Our sodium voltage-gated channels will open up right away, as opposed to our potassium ones that kind of open a little slowly and close a little slowly. And looking at the mechanism, here we're looking at our sodium voltage-gated channel. Sodium at rest, when our cell is at rest, our gate is closed. We've got an activation gate that's closed over here, and less importantly, we have an inactivation gate that's open over here. But at rest, what millivolts are we at? Negative 70. So therefore, it's closed at negative 70. And then when we open up, something that opens up would be the change in the voltage. Here you can see it's more positive on the inside. That's going to open up this channel that will allow sodium to rush in. And that gate flips open. Once we reach this certain threshold, it triggers open, and now we get even more sodium rushing in. So this change that's taking place beyond the graded potentials that are taking place in the cell body, we want to see what changes are going to take place at the voltage-gated sodium channels. And that's going to lead us into the action potential. Different than what we talked about in our graded potentials. The action potential is going to have a very different waveform, and these are going to involve those voltage-gated channels. So the next couple slides are going to take you through, and all I'm wanting to do here, my entire aim is to take you through and just show you the opening of the gates, or the opening of the voltage-gated channels. The first of which we're looking at, again, voltage-gated sodium and voltage-gated potassium are closed at rest. The next step we're going to look is called the initial depolarization. And if I could look at my curve right here, again, here's our membrane potential where we can see it in millivolts, and we can see what's taking place over time. And initially, when I get a ligand that opens up, or opens up one of those channels, you'll see that sodium starts to move in. And the movement of sodium channels causes the depolarization. That shouldn't be new news. That's our graded potential. If our sodium channels start to open up a little bit, here you can see we're going to get to a certain point where we reach a threshold at which we activate our sodium voltage gated channels. Okay? So we get a little bit of a depolarization once that we reach that threshold, and that threshold is about -55, which we'll talk about in a later slide. Once we activate those voltage gated channels, now all sodium can start rushing in through these channels. So now we get this huge rush of sodium going in. And what that's doing is causing what's called the rising phase. Here you can see we're going from -70, -55, then we're opening up those voltage gated channels. And take a look at where 0 is. See where that level is? That's where we're electrically neutral. Notice how we have this overshoot, right? So at one point on the inside, it becomes positive. So once we get to the top, once we get to the very top, and where we get up to is about +30. Once we get to about +30, what that's going to do is going to inactivate our voltage gated sodium channel. That gate closes. And now sodium can't go in. So the movement of sodium stops once we reach the very top. But what does open is our voltage gated potassium channel. And remember, it opens up kind of slowly. So at that point, these are fully open, and now we've got positive ions. We've got potassium moving out of the cell. Now that I've got a positive ion moving out of the cell, what is that going to do for the inside? It's going to make it more positive or more negative?
Negative.
More negative. So we're going to start to see the decrease, and this becomes the falling phase. So we start to come back down, coming down, and eventually we're going to make our way back to -70. So don't confuse us for thinking when you see the rising phase and then the falling phase. We're not reversing what we're doing at the falling phase. All we had initially was sodium moving in. The falling phase was potassium moving out. So if you were back at -70, we're not back at a resting membrane potential. Sure, we're back at -70, but the ion concentrations are different because we had potassium going out, we had sodium going back in. Now, what you'll notice is that we're going to continue repolarizing up to the point of hyperpolarization. And this is what's called the undershoot, where our sodium channels are still closed, but our potassium channels still remain open. So now we have more positive ions moving out, and this was part of your quiz question. An increase in the membrane potential difference, meaning below -70, is due to potassium still moving out of the cell. And at this point, once we get down to the bottom, now those potassium channels close, and then it's going to bring us right back to our resting membrane potential. All while this is happening, our sodium potassium pumps are continually moving stuff out, moving that sodium back out, moving that potassium back in. In this particular graph, I included this because this helps you kind of, by looking at the key, will tell you what's happening at each of the phases. And you can see what's happening in terms of our stimulus here. The stimulus, everything from -70, if you were to just memorize 3 key terms, or 3 key membrane potentials, -70 is rest, -55 is threshold, and +30 is the top of the phase. Here you can see, again, here's rest. Any stimuli that come in, anything that activates our sodium channels will start to create this depolarization. And by the time we make it over to the axon hillock, if that reaches -55, that opens up all those rich voltage gated sodium channels at that point, which causes that sodium to rush in. And then, this was when our potassium opens up, and then we do the undershoot, and whether you call it the undershoot or the after hyperpolarization phase, that's perfectly fine. And then we get back to our resting membrane potential. So that's not new, but the 2 terms that I want to introduce that are new are the absolute refractory period and the relative refractory period. So thinking about a refractory period is when, well, what do you guys think what a refractory period is? Think about when something fires, and then there's this period where that thing can't fire again. Right? That's exactly what a refractory period is. And let's first describe what's happening in the absolute refractory period. Looking at this point, we've reached negative 55 millivolts. This point right here, from this yellow to the slightly more yellow, is considered the absolute refractory period. The question is, why can't this neuron fire again during this period? Think about that. During this period, why can't you fire again? If this was our stimulus, and this creates that action potential where we reach threshold, and we have sodium already rushing in, we have potassium coming back out, why wouldn't another stimulus cause another action potential? The answer is much more simpler than you think. Yes?
Is there like something called like all or none, like basically let's say?
Kind of. You're getting there. You're getting there. It's a little you're a little ahead.
Because potassium channels are open now?
Not necessarily. It's even easier than that. It's because the neuron's already firing. It's already firing. So if you were to create another stimulus right here, it's already reached threshold. It's already fired. It has to go through the entire cycle in order to make its way back. Okay. So that represents, if this is our stimulus, we get a depolarization. At this point, once you get to that point that match finally gets that certain amount of heat, it's gonna fire off, and that match is already lit. Throw another flame in there, that match is already lit up. It's not gonna do anything. So now what we're gonna look at is the next phase, which is called the relative refractory period. And by pure definition, you'll see that on the next slide over, requires a stronger stimulus for the second action potential. Meaning that for a relative refractory period, in order to initiate another action potential, the stimulus has to be stronger the second time around. And let me explain what's taking place over there. Here you can see, and I want to describe it in this slide versus this slide where it might be a little less easier to see. The after hyperpolarization phase, take a look, we're at negative 70. In order to elicit an action potential, what membrane potential difference do we have to get from rest to negative 55? We have to go from negative 70 to negative 55. What's the millivolt difference that you have to get? 15, right? So this stimulus has to elicit a 15 millivolt difference in order to reach threshold. Take a look at what's happening at the after hyperpolarization phase. Let me give you a number. We're about negative 80 right here. If I were to create a stimulus right here, I'd have to go from negative 80 to negative 55. What's the difference there? 25 millivolts. So that stimulus, that second stimulus at the relative refractory period has to be a greater stimulus because we have to get us back up to threshold in order to elicit a second response, a second action potential. Does that make sense?
So refractory happens beneath the 70?
Yes.
Right.
Yeah. And here you can just appreciate that even though there's a little bit part of it, that's fine. It's pretty much the undershoot at which we would see the relative refractory period. Okay, what questions do we have about this?
Does this all happen in the cell body?
So where we were talking about sodium moving in,
Yeah.
we're getting to the axon hillock.
But we haven't gotten there yet, have we?
The whole purpose of this action potential, okay, the whole purpose of what we're really talking about is really what's taking place at the axon hillock. Once we reach threshold, we've got all these channels right here. Once that membrane potential that reaches those waves of sodium make their way over to the axon hillock, if that causes enough of a depolarization that we reach threshold in this area, it's going to open up all these gates so that it allows sodium to rush in. So that action potential is taking place at that one spot. Sodium rushing in, then you're going to see that at some point, right during this phase right here, at some point when we were negative on the inside initially, all up to that point, we were negative. At some point, for a brief moment in time, the polarity switches and it becomes positive. And what we're trying to do, once we've kind of lit the mesh right here, we want it to make its way across, and that's what we're going to talk about this second period when we talk about action potential propagation. Right now, I'm just talking about what's taking place at the axon hillock. What do I need to do to light that match? Does that answer your question? So now that you've understand it, and for the most part, what you should be able to understand by now is the movement of ions. If you get that, you're okay. If you start to understand more of the refractory period as to the mechanisms of why the refractory periods take place, where we have absolute versus relative, you're in better shape. But to get in really good shape, you have to understand permeability. Permeability is related to the ability for ions to move in and out, and that's all governed by the opening of channels. And in this case, we're talking about our voltage-gated channels. So this is basically the same thing of what we're looking at here, but we're going to introduce permeability. We're looking specifically at sodium permeability, that's the ability for sodium to move in, and then potassium permeability. And this helps you visualize, at least from the graph, at what points are our sodium channels most open, as well as the point at which our potassium channels are most open. And then the very bottom here, the green section, talks about the excitability, the likelihood that that neuron would fire. So starting off from our earlier point, here you can see we're at rest. And at rest we know the neuron is excitable. So here we can see the excitability is high. And once we reach threshold at the axon hillock, we'll see that's going to open up our voltage-gated channels, causing sodium to rush in. And at that point, we lose excitability because that neuron is already firing. And it lasts the entire period up to that point where we get, if this defines absolute refractory period, here you can see the relative refractory period. Let me save that for later. So in that initial rise, you can see we have sodium rushing in. And that should make sense because you'll see that the channels are most open right up to that point. More and more sodium channels are opening. And then once we get to the very peak, well, it's going to start to decrease. And that means at this point, more and more sodium channels are closing. All while that's taking place, our potassium channels are also rising, but it's rising right during the falling phase. So as more and more potassium channels open up, more positive ions are moving out, making it more negative, hence repolarization. And notice how once we reach this point, yeah, we're back at -70, but those potassium channels are still open, causing more potassium to move out, more and more to move out, eventually up to the point that we reach the end of absolute refractory period. Here we're still in the undershoot, and we're reestablishing back to where we started. And not until we start moving towards the latter end of the relative refractory period do you start to see the excitability start to climb back up. And just as we described earlier, here was about a 25 millivolt stimulus in order to result in another action potential. So as long as if I were down here and I reach back to -55, I could elicit another action potential. But as we get towards -70, we're back to where we started. All right, so now we got this video. And this video, hopefully will pop up. There it is.
Membrane is at its resting membrane potential. The activation gates of the voltage-gated sodium ion channels are closed, and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
Set up a little bit more. So now that we've described what's taking place in that axon hillock, let's start to talk a little bit more about the conditions that are required for action potential. And what we can first start off with is by looking at the graph on the bottom right. Here you can see the same membrane potential. Here we are at rest at -70. You can see the measured changes in our depolarization with the stimulus, the paired stimulus. So all of this is happening simultaneously. So here we're looking at is the first principle, which we call the all or none principle. And the general principle behind the all or none principle is that if we don't meet the threshold, an action potential doesn't fire. Once we reach threshold, then the action potential fires. So looking at this, here we see subthreshold stimuli. And that subthreshold stimulus causes a little blip, and that would be a small graded potential. And it doesn't result in an action potential taking place. It just comes out, it depolarizes, and then repolarizes, and that's it. If I were to take even a little bit more of a subthreshold stimulus, a little bit more of a blip, that's going to cause maybe even a little bit higher of a blip, but not quite threshold. Once I get to a stimulus that does elicit threshold, and that causes more sodium to go in, and once those sodium waves make their way down to and diffuse over to the axon hillock, resulting in a membrane potential at -55 at the axon hillock, that drives the action potential, and therefore this now lights up. So that's a threshold stimulus. Now the question is, what happens if I reach suprathreshold? Let's say I give you a really big stimulus. And to give you an idea of, if you want something that will at least help you think about the concept of driving an action potential. Let's think about your subcutaneous skin receptors. And let's think about pain. If you were to have something that just lightly touches your skin, do you think that receptor right there that receives the signal of something touching your skin, do you think it's going to make its way over to your brain for you to receive? I just got a dust particle that landed on my hand.
No.
Is that going to elicit anything? Probably not. Therefore, that's a subthreshold stimulus. Now I'm going to have something that barely pricks your skin, just enough to create an action potential. That action potential takes place here and sends all the way back over to the central nervous system. So now you're aware that's a subthreshold stimulus, just a little pinprick. Now what happens if I mash your fingers a bunch of times? What's the difference? It's still going to elicit an action potential. And if you notice the action potential, the magnitude of the action potential does not change. If you take a look, whoa, what was that? Sorry. If I were to take a look at my action potential, it rises up to +30 and comes back down. That's it. If I were to give it a suprathreshold stimuli, I'm still going to get the same waveform. An action potential still exists. So the question is, what's the main difference? What's happening to that neuron if I jabbed you with something, a suprathreshold stimulus?
You don't feel
a higher stimuli?
Not a higher magnitude. It just means that that neuron is going to fire a bunch of times. So in other words, suprathreshold stimuli results in increased frequencies of action potentials. Think about it. If I took something and stabbed your finger, those subcutaneous receptors are firing a bunch of times. And the number of times they fire for suprathreshold stimuli will signify how intense the stimulus is.
So it's just repetitive times hitting the threshold.
That's all it is. So with that, we can now kind of think about it in terms of, let me use another example. Let's think of a bicep curl, right? I'm holding a weight, and I'm holding a 100-pound weight, which I usually do, right? And I've got a stimulus, and that stimulus is the muscle contraction that needs to take place. If I have a subthreshold stimulus, can I lift the weight? Probably not. If I get to a threshold stimulus, sure, that's going to cause an initiation, but that's just one quick fire of that action potential. What's going to cause me to actually be able to lift it is constant firing. And we can see that in the next slide over. So now if you could take it as looking at the stimulus, and the stimulus in this case would be the firing of that neuron, the neuron that's leading to the bicep. We're looking at the action potential that's taking place between a neuron and a muscle. So the particular effector that we're talking about is not another neuron. We're talking about the muscle. So if you were to take a look at that first stimulus, that would be the first twitch of that muscle fiber, you'll see that'll create a contraction and then a relaxation phase. And that's one stimulus. If we were to take a look at what would result in a higher tension, so this just elicits just a little bit of a tension, maybe just cause a little bit of a twitch. What I need to do is I need to generate maximal tension in order to elicit that major contraction that I need in order to lift the weight. Okay? So what I'm trying to get to is, here if you see the stimulus taking place, here's a second stimulus. That's going to elicit another one, another little twitch. And what I'm doing here is increasing the number of twitches that are taking place, the stimuli, in order to elicit what's called summation. And summation is exactly what the term insinuates, is the additive effect of stimuli resulting in multiple action potentials that, on the effector, results in increased muscle tension. And that should make sense. If I'm trying to get that bicep to lift that weight, I need to have that CNS constantly stimulating and firing that neuron to constantly fire action potentials to result in more contractions that add up. So this is what we call summation. And when you look at repeated stimuli, you'll see that the muscle contraction starts to increase. We start to get a fast rise in tension. And if you have maximal firing stimuli, you'll see what's called a complete tetanus. That is a smooth, generated increase in muscle tension to get us to maximum. So that kind of helps tie in, at least to take a look at what's happening at what's called the neuromuscular junction. That's the neuron up to the muscle. But all of this is tied into, if you were to understand the suprathreshold results in increased frequencies, and that's how we're able to differentiate things above threshold, is the rate at which those fire. Anything below subthreshold, or anything below threshold rather, any subthreshold stimuli result in little graded potentials up to the point that we get to threshold, and that's our action potential. And that's how we get that neuron to fire all the way across. All right, so this, I would highly suggest that while you guys are doing your studying, is to go through and compare your graded and action potentials to understand what's taking place. Some of the key things that you're going to see here are the origins of where our graded potentials take place, mostly in the dendrites as well as the cell body. If you were to take a look at the types of channels for graded potentials, these are our ligand-gated, our neurotransmitter binding gated channels, as well as mechanically gated ion channels. We didn't really talk much about mechanically gated. Those are going to be our sensory neurons that we'll talk about in next week's lecture. When we look at the amplitude, for the most part, are subthreshold, anything below negative 55 millivolts. Our graded potentials can either be depolarizing if we get sodium moving in, or they can be hyperpolarizing if potassium moves out, depending on what neurotransmitter is binding to which channel. And then action potentials, you'll see that takes place along the axon, starting at the axon helix, the most sensitive area with the most voltage gated channels. You'll see that this action potential, once generated, we'll be able to see that propagates all the way down. You can see the size, the amplitude of the action potential. if we're starting from -70, we get all the way to +30. So the amplitude of that action potential is always going to be -70 up to +30, 100 millivolts. And when you look at the rate at how fast an action potential takes place, it's fast. Much faster than what you would see in a graded potential. And the waveform for the action potential is always the same. You see the rising phase, falling phase, the undershoot, and back to where it's at. What we're going to do is we're going to now talk about the action potential propagation. This entire time we've been talking about the generation of the action potential at the axon hillock. But now that we've lit the fuse, we want to be able to see how that action potential makes its way down to the end of the axon terminal, where we have our synaptic bulbs filled with neurotransmitter. So when we look at action potential propagation, we're going to be looking down the length of the axon. And what this is talking about right here is looking at the action potential, let's say right at this point. We've got an action potential that's supposed to move down at this point. Our voltage-gated sodium channels that are present all throughout the length of the axon. When we're looking at this point of time, we're going to see sodium rushing in. And when sodium rushes in, it's going to diffuse all along that area. It's going to move both this way, and it's going to move both this way. Just like that earlier slide that I'd shown you. Now, if we were to look at the changes that take place, once that sodium comes in, that's going to cause us to reach threshold in this next adjacent area down the line. Once sodium rushes here, we get enough sodium that it reaches -55. That results in another action potential. But notice how I pointed out that sodium travels both ways. The question for you guys is, why doesn't it cause an action potential to take place prior to this point? If I have sodium coming in and it diffuses all around that area, this part lit up right in the front, but this part right here doesn't.
Because it's already started.
One more time.
Because it already started.
It started here, but it's finishing over here. And what was that phrase Yeah, you're getting there.
Hyper something?
This area prior to is an area that's in hyperpolarization. It's in refractory period. That's a term I'm looking for. It's in refractory period, meaning it can't fire again. And that's what we're looking at over here. So instead of looking at my crummy drawing over here, let's take a look at how it looks like over here. So at this point, you see the channels are open. We have sodium coming in. And it's going to diffuse both in all different areas. It's like that pebble that I talked about, throwing into a pond. It's going to move in all directions. Except in this area right here, back over here, this area is already in the refractory period. This part lit up, then this part lit up, then this part lit up. At those points, if this is in refractory period, it cannot elicit another action potential. The only other place that can is in an area that's not quite depolarized yet. So therefore, if you were to take a look at this fuse, it only moves in one direction. And that's what's going to govern the propagation of that action potential down the length of the axon. To give you a better example, I've got a video for you.
This length of axon can be likened to a piece of fuse. The burning match under the axon represents an electrical event that generates an action potential. This event normally takes place at the axon hillock. Recall that to trigger an action potential, the electrical event must depolarize the axonal membrane beyond its threshold. That is, the membrane potential has to become positive enough to initiate the action potential, which is an all-or-nothing event. Once the membrane reaches that threshold, voltage-gated sodium channels open up, and sodium rushes in, as reflected in the upward deflection of the membrane potential. But how is the action potential propagated down the axon? Look at the area just ahead of where the action potential has just fired. It is becoming more depolarized. A millisecond later, the positive charge associated with the first action potential has spread to an adjacent region of the axon. This area reaches its threshold, and this segment of axon fires an action potential. The area of axon that fired an action potential a millisecond ago cannot become depolarized now. It is refractory because its sodium channels are inactivated. In this way, the action potential propagates in only one direction, like a fuse. Now, 2 milliseconds later, the positive charge spreads to the next adjacent region of the axon, and it reaches its threshold and fires an action potential. The region of axon that fired a millisecond ago cannot be depolarized. It is refractory. The area of the membrane that fired 2 milliseconds ago has now returned to its resting potential, but it is too far away to be influenced by the current action potential. In this way, the action potential migrates, like the fire on a fuse, toward the axon terminal, where it is delivered to another neuron. Now let's watch the whole process at high speed.
So you guys should see by now, the ultimate goal is to propagate that action potential all the way down. That point where we're going to see the inside becomes positive. It becomes positive for that period right there where we reach that overshoot, that point where we're at the rising phase and we're above 0 millivolts. And as that propagates all the way down, you can see what's taking place is the movement of that action potential. So the continuous conduction, when we look at the mechanism at which we see action potentials move down, we can see that that action potential can be conducted in 2 different types of axons. We've got our first bit that's called continuous conduction, and that involves unmyelinated axons. And if you remember what in our central nervous system, we had oligodendrocytes that would wrap around the axon, creating myelin sheathing. That's what we're going to be able to see in the next slide over, which is called saltatory conduction. So looking at continuous conduction, if you were to take a look at the entire length of that axon, you can see that all of those voltage-gated channels are equally distributed all throughout the length of the axon. And that means as this portion lights up and we get sodium rushing in, the prior portions being in refractory period, we see this wave of depolarization as it moves down the axon. And it moves through continuously, just like that bomb fuse analogy that last guy was using. Just shows that it moves continuous all the way through. And if you were to take a look at the speed of it, the speed isn't very fast. It's fast, but it's not quite fast. It can cover that length of 1 meter of axon. We've got axons that are very long. About 1 meter, they can cover it in about 100 milliseconds. And in order for that to propagate, again, depolarization to threshold, depolarization to threshold, depolarization to threshold, all the way through up until the point that we reach the axon terminal. Now, if you were to take a look at saltatory conduction, again, oligodendrocytes that come in and wrap that myelin sheathing in the central nervous system. We have Schwann cells in the peripheral nervous system that come in and wrap that myelin sheathing. And what is the entire purpose of that myelin sheathing? Well, it's basically insulation of a wire. It comes in and creates this fatty layer. And what does that do? Well, now we have these nodes in between called the nodes of Ranvier. And they're going to have the highest concentration of voltage-gated channels on them. And in those areas, you can see what's taking place is that the depolarization jumps. We don't have any voltage-gated channels in between where we're wrapped in myelin sheathing, and that simply prohibits sodium from moving in. So the question, how does it propagate? Well, in these areas where we have high density of voltage-gated channels, we have sodium rushing into the site, and then it's going to move down through conduction of sodium all the way through. And this is just the movement of axoplasm. As it moves through, it's going to move to the next node, and then once that depolarizes this area, we're going to have sodium rushing in again. Then it's going to move down to the next, sodium rushing in again. And it's much more energy efficient this way. Why? Because all along this entire area, we're going to have sodium-potassium pumps bringing that sodium back out, bringing that potassium back in. And those sodium-potassium pumps use ATP. So if you only do it in the areas that they're most concentrated in, and just allow sodium to move through those through the axon in between the myelin sheathing, then that's less ATP you get to use. So that signal literally just jumps from node to node. Not only is it much more energy efficient, it's faster. You don't have to rely on sodium coming in. It will just move from point to point. So that is saltatory conduction. And you can see that on the next slide over, where you'll see those action potentials jump from node to node. You might see a little bit of a degradation of the signal, but for the most part, sodium is moving efficiently through. That fatty insulating layer prohibits any movement of ions, so it only moves in one direction. And eventually, this area depolarizes, causes another action potential. Move all the way down, cause another action potential. So, in essence, what's happening as it moves from node to node, that action potential causes it to jump, causes it to refresh, and cause a whole bunch of sodium to rush in to result in that action potential taking place. So looking at this, if you were to take a look at the rate of impulse conduction, how fast would it take for that action potential to move through? Which would be faster? Well, we already pointed out that that saltatory conduction is much more energy efficient and it's faster. In fact, myelin makes it about 5 to 7 times faster moving down that axon. One of the ways of looking at this is to think about the whole concept of pain. Acute pain, something like a quick stabbing on that finger, moves through saltatory conduction. It moves very quickly to make its way over to the central nervous system. But if you were to take a look at chronic pain actually utilizes axons of continuous conduction, where it moves very slowly. Hence, if you were to think about the difference between chronic pain versus acute pain, there's a very big difference between a sharp stabbing pain versus something that's very chronic and dull, like low back pain. Another thing that also affects the rate is the diameter of the axon. For the most part, neurons already kind of have very minute differences in the diameter, so that's not really going to govern too much. The bigger the diameter, the faster those ions move through. And that will make much more sense, especially when we talk about our cardiovascular lecture. Temperature. What does temperature do? Now go back to our early lecture before. What is an increase in kinetic energy due to temperature do to ions? Speeds them up, right? So now if you can imagine, back in saltatory conduction, if I apply heat to a neuron, that should get my sodium to move across faster. And if my sodium moves across faster, that causes my signal to jump even faster. Now let's think about something that you can apply for the converse of this idea. What happens in the cases of pain? Why would you apply ice to a site of injury? It's not necessarily just the inflammation, which essentially ice would
To slow down the
lower the speed of ion transfer through the neuron, right? So cool it down, and sodium moves even slower. That's why you would want to apply ice, cool that area down. So temperature, the increase in temperature would increase, while the decrease in temperature results in a slower.
So why would you want to add a hot pack if
What's
it's
that?
increasing the temperature, a hot pack?
Why would you want to add a hot pack?
Yeah.
Well, there's theories behind adding hot packs that would increase blood flow to the area, and you're not relying just on hot packs. You kind of do an alternation between hot and cold. That's more like physical therapy that I don't really delve into. But when you think about why the mechanism as to why ice works, it's exactly that: to slow the rate at which pain conduction takes place up towards the central nervous system. The thing that does not affect the rate of impulse conduction is the stimulus strength. As long as we get our neurons, those sensory neurons, to get to threshold, it's going to travel at the same speed. Whether you're in a continuous, as long as you're in a continuous, it's not going to speed up any faster. If in saltatory, it's not going to speed up any faster. It's always going to travel the same speed. All of this that's been taking place so far has been electrical communication. And electrical because we have ions of charged nature. We have cations that are rushing into the axon. And the movement of sodium as it moves all the way through is going to create that action potential all the way through. So now what we look at in the synaptic communication is everything that takes place between the neuron and the next effector cell, whether it's a muscle gland or a neuron. So before we get to that, we do need to talk about how all the neurotransmitters that are stored, we get neurotransmitters that are stored at the axon terminals. We have to talk about how those neurotransmitters are released. And then we hone in our focus on what's happening on the inside, which we refer to as the synapse. What exactly is a synapse? It's a junction between two neurons. That's basically it. So what we've talked about was the action potential propagation. We're good there. And we get to conduct that action potential down to the synaptic terminal. And what's happening specifically at the synaptic junction in between two adjacent neurons. And when we look at what we're referring to here, this is typically called the presynaptic neuron. And this is the postsynaptic neuron. And this right here being the synapse. And this is how we're going to be able to get one neuron to communicate with the next. We have a site at which we have communication. We're seeing the two types that we have here. We have electrical and we have chemical. And chemical being the most common type. And that chemical communication that takes place comes in the form of a neurotransmitter. A neurotransmitter that's exocytosed at the presynaptic neuron and diffuses it down its gradient over to the next. And so you'll see we have chemical, which we're going to be talking about. We do have electrical, which I'll talk about in a later slide. If we look at some of the connection types, you can see that axons typically will terminate at another dendrite of an adjacent neuron. We've got axon to axon, and then we've got some that are axon to the cell body. But really the heart of it is looking at axon to dendrite. That's going to be our most generic example that we're going to be using. The axon, which is going to be the transmitting end, to the dendrites, which will be the receiving end of the adjacent neuron. The neurotransmitters that are released from the axon terminal, for the most part, can be excitatory or inhibitory. It depends on what those neurotransmitters are. Again, I haven't talked about how we release the neurotransmitter. I'm just talking about the neurotransmitters themselves. So looking at the chemical, on the chemical makeup, and we'll talk about the different types of neurotransmitters, can either depolarize or hyperpolarize the postsynaptic neuron. So excitatory postsynaptic potentials typically make a neuron much more sensitive, more likely to fire. On the other hand, inhibitory is the exact opposite. With those types of channels, here you see you're hyperpolarizing it. Just like what we saw with the refractory period, we saw we're below resting membrane potential. So it's going to take an extra effort to bring us back to resting and bring us up to threshold in order to elicit an action potential in the postsynaptic neuron. When we look at all the neural activity that's taking place on that postsynaptic neuron, what we're doing is we're looking at the additive effect of all of those neurotransmitters that are being released. And that term that we look at is called summation. Same term that we saw earlier, but summation in relation to what's happening in the synapse. And that is the sum of all excitatory and inhibitory postsynaptic potentials. So let me take a look at another example. Here, I can take a look at a neuron. Here's another neuron. And I've got one bigger neuron. So I've got two terminals onto one neuron. I can have one that's excitatory, and I can have one that's inhibitory. If this one creates a 15 millivolt, and this one creates a negative 15 millivolts hyperpolarization, this should sort of cancel each other out and leave this resting membrane potential back at where it's normally at negative 70 millivolts. So that's a concept of summation. And we'll be able to break down what summation is. This is one type of summation. There's another type of summation that we'll talk about. So looking at these, here postsynaptic potentials can either depolarize or hyperpolarize, which is not new news. This talks about a stimulus that is excitatory, which results in an increase in, depolarization. Here we see an inhibitory postsynaptic potential where it's IPSP. You add those two together, they cancel each other out. So the two types of summation that we can look at, we can work either with space or time. And let me use an analogy that I know works better than the ones I've used today. Think of somebody that's sitting next to you, and you're sitting there and you're trying to pay attention, and somebody starts poking at you, okay? And you know you're good, you're sitting there, you're fine, you're not excited, somebody's poking you, right? Spatial is where you have the summation of postsynaptic potentials from different locations on the postsynaptic cell at the same time. That means you have two people poking at you, up until the point that you reach threshold and you fire off and you do whatever you want to do, okay? Now temporal is the summation of postsynaptic potentials at the same location at different times. So that's someone poking you repeatedly, up until the point that those summate and you reach threshold and you do whatever you do, whether it's a backhand or forehand, whatever it is, okay? So looking at these, you can see on the graph at the bottom right, here you see an example of spatial summation. You have stimulus number 1 and you have stimulus number 2. This is the example that I was talking about earlier. Two presynaptic neurons firing onto a postsynaptic neuron. And if they're both excitatory, you can get one, wait, this is spatial? Yeah, this is spatial summation. From different locations at the same time. This is the stimulus that would result from one. This is the stimulus that would result from the second. But you get those two to fire at the same time, and it brings us up to threshold. So this could be a 7.5 millivolt stimulation. This could be another 7.5 stimulation. Add those two together, brings us up to negative 55, results in a firing of an action potential. Now looking at temporal, on the other hand, this is where we get that additive effect of that one presynaptic neuron firing multiple times, and since that presynaptic neuron is still adding up, this is summation. Summation up to the point we get to threshold, we fire again. The electrical synapses, because these are synapses where we have gap junctions. So we get the direct movement of ions moving through. This is purely electrical. We don't really cover this until we get into our cardiac cells. Cardiac cells talk about the movement of ions in between cardiac muscle cells. Okay? And the advantage of this is we're not relying on any molecular diffusion across that synaptic cleft. It's purely ions moving through those gap junctions. Again, we'll talk about that later. So now that you know the principles of postsynaptic potentials, and again, the main purpose of adding those potentials would mean firing of that postsynaptic potential, making it to its next effector target. Let's take a look at how we get those neurotransmitters released to elicit either an IPSP or an EPSP. The whole principle, and I kind of go over this in multiple slides. Let me just kind of give you the gist of what's happening. In this portion of the axon terminal, we're going to be looking at our third voltage-gated channel. I know we talked about sodium, we talked about potassium. The third one in this case is going to be calcium. And this is the only place where we're going to be seeing calcium, voltage-gated calcium channels in the neuron. When that action potential makes its way down to the axon terminal, we're going to be depolarizing in that area that's going to result in the opening of our voltage-gated channels. And looking at that calcium is going to come in, and that calcium is going to have one specific role. And what it's going to do is it's going to start that process of the release of neurotransmitter. Calcium comes in, and it's going to dock with these vesicles. These vesicles are filled with neurotransmitter. And for this, you have to think about what we talked about last week. We talked about neurotransmitters, and in most cases are going to be some form of protein, or amino acid, peptide, or a protein that's manufactured with ribosomes, our endoplasmic reticulum, and packaged by the Golgi apparatus into these vesicles that are ready to be released across the synaptic cleft. Calcium comes in. Here you can see calcium rushing in. You've got these active vesicles that are filled, and here's our cell membrane. You can see that calcium comes in and binds to these docking stations that are these proteins right along the intracellular side of the cell membrane. So you'll see these vesicles that are filled with neurotransmitter come in, calcium binds and undocks these two proteins. And it literally will just break that point right there to cause exocytosis of those neurotransmitters. So that docking that takes place allows that to be released. Here you see dynamin and clathrin. You don't have to understand that process, but here we take that vesicle and we recycle it for that process again. So that's all it is. If you were to look at where calcium comes in, calcium works exactly in that mechanism, just to release those neurotransmitters in those vesicles. That's all it is. So these vesicles, if you were to take a look at these vesicles, they're already ready filled. We've got three types, and which you don't need to know, but three types of vesicles. They're already ready to be filled. You've got neurotransmitters that are being remanufactured and filling up these vesicles, and then we've got a reserve tank of neurotransmitters. So we've got plenty of neurotransmitter to be released, as long as we get calcium that's been entering the axon terminal. That's going to release these neurotransmitters to make their way across the synaptic cleft to bind to the channels that we talked about earlier. So if you get a neurotransmitter that binds to a receptor, and each of these neurotransmitters need to bind to a receptor that's part of that channel. So as long as that neurotransmitter binds to, you get that channel that opens up, and that either allows sodium in, or for an inhibitory neurotransmitter allows potassium out, or allows chloride in. So with that, now that we've understand the concept of how we release the neurotransmitters, let's take a look at the chemical nature of the neurotransmitters themselves. We've got lots of neurotransmitters that we've studied over the years. You can see the same mechanism that works. The release of neurotransmitter, the same mechanism, the release. The biggest difference is what is going to happen on that target, whether we're going to depolarize or hyperpolarize. If you were to take a look at what the effector cell is, if the next target is a neuron, we're going to result in another action potential that should take place on that neuron to move down the line. Okay. If you see the effector being a muscle, the muscle is essentially supposed to contract. So we need to release this neurotransmitter to make its way across, either to release an action potential or a contraction for another muscle. Some other of these neurotransmitters rely on a second messenger system. You get a neurotransmitter that binds, causes an activation. We don't actually get an ion to move through. What it's going to do, it's going to elicit a change that's taking place on the inside that results in what's called a second messenger. And we'll talk more about this in our endocrine lecture, but that neurotransmitter doesn't allow anything to take place. We get communication that takes place on the intracellular side. Here we would see something called cyclic AMP. This is an intracellular signal. It only happens on the inside of the cell. So that's what we're talking about. We'll go into more about that in our later lecture. So looking at our first neurotransmitter, the most common one that we're going to be able to see in a neuromuscular junction, that's a neuron targeting a muscle, is acetylcholine. Okay? Acetylcholine in neuromuscular junction is for the most part excitatory, or it can be inhibitory, depending on the location of the receptor. So anytime you have acetylcholine that's being released as a neurotransmitter, you have to have an acetylcholine receptor that picks up acetylcholine. Taking a look at acetylcholine, you'll see that acetylcholine is just an amino acid. You'll see the structure on there. What's interesting about acetylcholine is they first studied it way back when. It was back in 1915 when they first studied neurotransmitter. And they worked with cardiac muscle cells. And what do they do when they see cardiac muscle cells? They have it's supported with enough glucose, supported with enough oxygen. You have these cardiac cells that are still beating in a petri dish. So one of the first things they did in order to study neurotransmitters is they tried acetylcholine. They looked at some of the other receptors on here. And if you take a look at the receptors, there's ways to block those receptors that would result in the interruption of that chemical signal. So acetylcholine needs to be released by the presynaptic neuron, needs to diffuse across the cleft, and it needs to bind to a receptor. Now there are diseases, and if you remember when I used that term channelopathy was the pathologies of certain diseases, the etiology of a disease, the cause of the disease that causes some dysfunction in that system. You'll see the receptors could be interrupted at some point that would not cause that signal to take place on the postsynaptic neuron. So in order to stop that signal, I can either inhibit the production of acetylcholine or I could inhibit the receptors. This gives rise to some of the autoimmune diseases that result. And the first one of these are called myasthenia gravis. And typically what you would see with these people that have myasthenia gravis is it's a progressive muscle weakness disease. And the first thing you'll see is the droopy eyelids. What's happening with people with myasthenia gravis is that they get this progressive disease that starts with muscle weakness, that starts with the eyes, and eventually works its way down to more of the vital organs, and eventually will start to cause a heavy decrease in the quality of life. And in myasthenia gravis, the immune system comes in and destroys the receptors, the reception of the signal of acetylcholine. So what typically happens with these receptors, here you can see normal receptors. You have acetylcholine that diffuses across and binds to those acetylcholine receptors. You have your autoimmune disease that comes in and you get these antibodies that bind to the same sites where you have acetylcholine binding to. So in essence, this works. Going back to an earlier lecture, the antibodies bind competitively at the same active sites for acetylcholine. And if it binds to, acetylcholine can't bind to. And if acetylcholine can't bind to those receptors because they're blocked by those antibodies, then the contraction doesn't occur. So what do? They have certain drugs called anticholinesterase. And if you take a look at the term, choline, acetylcholine. ACE, right? ACE being an enzyme. Anticholinesterase is an inhibitor of acetylcholine. Acetylcholinesterase is an enzyme, bless you, that breaks down acetylcholine in the synaptic cleft. So when we release acetylcholine, it comes in, and you'll be able to see on the next slide, a couple slides over, this is how we remove the acetylcholine. Now, if we can inhibit the enzyme that breaks down acetylcholine, then we have more acetylcholine in the area that can bind to some of the receptors and still create that contraction. Okay. That'll make sense when we get to a couple slides down. The next one are amino acids. And the two main amino acids you'll see are glutamate and aspartate. Glutamine is something that you would see that's excitatory in the central nervous system. Taking a look at those neurons, most of the neurons in the brain are excitatory whenever glutamate is involved. If you were to take a look at GABA, GABA is gamma aminobutyric acid, and that is an inhibitory neurotransmitter. And if you were to sprinkle GABA onto the neurons, you would notice in the brain that would be inhibitory. So what that does is with the IPSP, that stops the action potential from taking place on the postsynaptic neuron. And again, looking at some of the other diseases that we've ever looked at, when we studied ADHD, attention deficit hyperactivity disorder, we saw that glutamate receptors were linked to hyperactivity. So it was the inability to inhibit our glutamate receptors that resulted in excessive activity, okay? Hence the hyperactivity. Looking at schizophrenia. Schizophrenia is linked to the expression of extra glutamate receptors. And if we know glutamate is excitatory, some of the neurons are supposed to be inhibitory. So if I express increased glutamate receptors, that makes our inhibitory interneurons much more inhibitory, resulting in imbalance in the postsynaptic potentials that are supposed to take place. So you see that a lot of these balances, a lot of these diseases are all related to the channels themselves. Other ones that we're looking at are modified amino acids. Take the amino acids, you modify them a little bit, and now you've got two main types. Catecholamines is a term that I'd like you guys to be familiar with. Catecholamines are typically things that speed the system up, things that you'll be able to see that are excitatory. Norepinephrine, epinephrine. Another term for epinephrine is adrenaline, okay? And dopamine. So these are catecholamines that we'll be referring to quite a bit in our later lectures. that stimulate the sympathetic nervous system. If you were to take a look at the role of norepinephrine, you'll see that it's evolved in arousal, awakening, regulating mood. If you take a look at epinephrine, adrenaline, that increases the fight or flight response. Again, do you guys remember Pulp Fiction? What happened they did with, I forget what's her face. She had an overdose. They injected her with adrenaline right straight to the heart. Fight or flight's response caused the heart to beat harder, caused the sympathetic nervous system to pick right back up. Look at EpiPens, for instance. EpiPens that I know that have gone up in price. EpiPens are supposed to stimulate the fight or flight response, which is going to increase the ability for air to move into the lungs. It causes bronchodilation for people that have anaphylactic responses. Dopamine, if you were to take a look at dopamine, dopamine is tied into that pleasure response area. And again, one of those things that if you look at those areas, it also is involved in skeletal muscle tone. So if you're looking at emotional response and then skeletal muscle tone, remember dopamine is also released. It's a neurotransmitter, but we've got neurons all over the place. Whether they're involved specifically in areas such as the substantia nigra, parts of the brain that we'll talk about later on. Dopamine has a response there. Dopamine has a response in other areas of the brain, the pleasure center. When we look at serotonin, serotonin is derived from a modified tryptophan. Okay. Here that serotonin is related to sensory perception, temperature regulation, mood control, appetite. It's all enhancing these things. While on the other hand, serotonin, depending on where those neurons are, can also affect sex drive. So it's not uncommon that people that take any sort of serotonin or any drugs to increase their serotonin can also result in decreased sex drive. So these things are heavy. When you look at certain drugs that affect neurotransmitters, they have varied side effects depending on what other areas of the brain they affect. Other areas that we can talk about, ATP, nitric oxide, don't worry about that. We'll talk about that later on. But just to give you an idea that we just don't have just amino acids, there's many other ones. Are much lower. So in effect, what we're trying to do with these types of drugs is to raise the amount of serotonin back to the normal levels. Okay? If we can raise already low levels, then somehow we can be able to do that. So the drugs look at these particular mechanisms that we have in place. We have two different types. We have SSRIs and MAOIs, of which the first is called selective serotonin reuptake inhibitors. I know that's a mouthful, but let's take a look at exactly how that works. So the first thing you can see on here is what happens when you get serotonin released into the synaptic cleft. We have serotonin that's released, it binds to a receptor, and then once that serotonin is out in the synaptic cleft, it can get taken back up through what's called an autoreceptor that shuttles serotonin back into this presynaptic neuron. Well, in people that have depression, if serotonin is already low, what we could do is we could block the reuptake through an inhibitor, right? A competitive inhibitor called an SSRI that binds to that reuptake inhibitor, therefore effectively allowing serotonin to stay in the synaptic cleft a little bit longer. So that mechanism increases the amount of serotonin in that way. And some of the drugs you'll see there, Prozac, Paxil, Zoloft. The other mechanism are called monoamine oxidase inhibitors. If you look at the term monoamine, this is exactly when we look at what serotonin is. A modified amino acid, a monoamine oxidase, which is an enzyme that breaks apart that enzyme. So here you see this, and I forgot the name of it. It's an enzyme called COMT that for serotonin, this enzyme comes in and breaks it apart into its smaller constituents. So if we can take an inhibitor of that enzyme, that should allow more serotonin to remain. So typically people, when they look at these types of drugs, selective serotonin reuptake inhibitors, typically we'll also tell them, you're not allowed to take these types of drugs, because that could cause an overshoot, an increased amount of serotonin. And all they do when a psychiatrist gives you an SSRI, typically what they do is they taper to see what they can do on the reuptake. They can block the reuptake to see how much serotonin is up. So they'll up-titrate you to see when you get to the point that you exhibit the least amount of symptoms. So in this case, what we're doing with depression is not necessarily treating depression, but we're finding ways that we can sort of treat the symptoms of it. So by bypassing any other measures, bring serotonin levels back up. Yes?
So SSRI just slows it down from kicking in?
Yeah.
The other one just breaks it down?
And the other one, monoamine oxidase inhibitors, just blocks that enzyme from breaking it apart.
It blocks it.
Yeah. Yes?
Well, I heard they're actually like leaning away from MAOIs nowadays because they have more side effects and the consequences are pretty severe. And like in the last 20 years, I believe, you've been prescribing more SSRIs.
Yeah, there's not too much of a focus on these because when you look at these enzymes, you're basically breaking it apart. They notice that there's a lot, when they start to study a lot more about signals that go backwards. Everything we've been talking about signals going down, but we're starting to learn more about retroactive signaling. So that's why they're starting to do more of the reuptake inhibition. Because that allows, at least we're not breaking down serotonin, it's still being reused. So, like effects, depending on where those enzymes, that enzyme inhibitor that they give you can work against you, can affect other systems as well that utilize those same enzymes. Yes? All right. So, looking at these, well, let's take a look at, while we're looking at some of the other pharmacological treatments, let's take a look at some things that actually work against you. And the first one is called botulinum toxin. And this is produced by a bacteria. It's an anaerobic bacteria that forms these spores that is actually infected by another virus that affects that bacteria. So it's a fairly cool concept, but this bacteria you can typically find in soil, you can find in a certain gut of certain mammals, and you can also find them actually in our environment, in streams and lakes. And the way these things work, specifically, is it inhibits acetylcholine production. While you saw with myasthenia gravis, that affected the acetylcholine receptors. So acetylcholine couldn't bind. Here, botulinum toxin works specifically in breaking apart the production of acetylcholine. Not the actual production, but of those vesicles. So you don't need to know the mechanism here, but specifically where what you would normally see is a synaptic vesicle that's filled with acetylcholine. We have these docking proteins right here that typically will, when in the presence of calcium, will allow this vesicle to be exocytosed into the synapse, allowing acetylcholine to bind. Acetylcholine binds to the muscle, and then the muscle contracts. Now, if you take a look at the toxin, what the toxin does specifically is it injects this enzyme that comes in that cleaves these snare proteins. And it comes in and it breaks it apart so that, and here you can see the botulinum toxin comes in, makes its way in, and then it expresses the gene for the production of these enzymes that cleaves all these proteins apart. Therefore, you have all these vesicles that are filled with acetylcholine that can never leave the presynaptic neuron. Acetylcholine can't make it across. The unaffected receptors here have nothing to bind to. And if nothing binds to it, then the muscle never contracts. So they've seen these, and in fact, any Botox or botulinum toxin that comes in excess can start to affect the skeletal muscle and affect the smooth muscle, and eventually affects the diaphragm and prohibits you from breathing. Okay, the diaphragm can't contract anymore and can't eject any air. So what you're looking at here are, and this is kid's alive, by the way. Don't think that he's dead or anything. But these are some of the effects that you typically see. You would see the first effects of Botox poison or botulinum poisoning by looking at the eyes. The eyes are droopy. You can see the eyes on there, the pupils enlarged, and just there's no motor function whatsoever. Luckily, he was breathing and most likely able to survive this. But they found that back in 1989, by looking at this mechanism, thought, well, if you can get muscle to not contract anymore, this could potentially work with other diseases. Looking at people with cerebral palsy, you would see people that have very tonic contractions of the extremities. And if you can inject the same toxin to be used locally on that muscle, you can inhibit the contraction, allowing them to relax that muscle. And so back in 1989, there was a plastic surgeon that thought, let me take that same toxin and use it in the areas in the facial muscles. Because typically what we see with the presence of wrinkles are subcutaneous muscles that cause wrinkles, cause contractions in those areas. So what he did was injected very small, minute amounts of that toxin that would relax the muscle. And so when you look at anybody that's ever had Botox, you're essentially injecting a toxin that prohibits the muscle from contracting. They've used it also in 2010, they've used Botox for people with chronic headaches, migraines. They found they can also do injections of Botox in certain areas to relieve some of that contraction. They've also used it on people with extremely sweaty armpits, something that they call severe primary axillary hydrohyphosis. They can do, again, injections of Botox into those areas to loosen up some of the muscles that prohibit excessive sweating. Poisoning, otherwise known as rat poison. Okay? So the way these work, looking at the particular cells, you'll see what are called Renshaw cells. And normally, Renshaw cells release this inhibitory neurotransmitter called glycine. And it makes its way into the synaptic cleft, and the glycine receptors that come in will prevent muscle contraction from taking place. So it inhibits the muscle from contracting. And so what happens with strychnine? Strychnine comes in, and anytime anybody's exposed to strychnine comes in and inhibits those glycine receptors, so that you don't have that inhibitory neuron that can inhibit the muscle from contracting. So essentially what happens with exposure to strychnine is that you get these massive contractions. You have no way of inhibiting that contraction from taking place. And so what you start to notice is how rat poison specifically works. It causes the diaphragm, diaphragm normally contracts, and then when you want it to not contract anymore, which we'll learn in our respiratory lecture, you need to relax the diaphragm. But strychnine comes in and inhibits that process, so the diaphragm stays contracted, that rat takes its last breath in, and can't release the breath back out, and therefore dies of suffocation. So here what we're looking at is knowing that the diaphragm is affected. The first symptoms that you can see with strychnine poisoning, rat poisoning, is facial muscles. Facial muscles are typically the first ones that are going to exhibit that process. And you start to see that the facial muscles will start to contract, and you can't inhibit those. And you see what's called a condition called rhizus sardonicus, which is called this rictus grin. It's this huge grin, the sustained spasm of these facial muscles, where you see the eyebrows majorly contracted. You see the rise of the eyebrows. You see the cheeks pulling back. An example of strychnine poisoning. Another thing for all you comic book nerds, Joker had this Joker gas, if you remember. And one of the things that was on it was it had strychnine in it. He actually mentioned strychnine and something else. I forgot what else was in it. But what happened with people that were affected by this gas is they had that Joker smile, what they also call the sardonic smile. Sardonic smile is exactly this. Hence the term rhizus sardonicus. That's where the term sardonic smile comes from, is that type of smile. So all of his victims that were affected by him all had that Joker smile. Another thing to look at is ethanol, which you already learned is ethyl alcohol. And this specifically works as a central nervous system depressant. And what it works on is it works on GABA, which we already established is an inhibitory neurotransmitter. And so what ethanol does is it increases the effect of GABA. It makes it much more effective as an inhibitory neurotransmitter. And GABA is supposed to bind to cause inhibition of the next postsynaptic neuron. And what it does is it has a twofold effect. It increases the effect of GABA, making inhibition much more increased. And then it also decreases the excitatory portion, glutamate. So looking at this, you can see where GABA is affected. Now, with this increased excitatory effect of inhibition, you see that that's what alcohol does, is it increases the amount of inhibition. Now, looking at the other sites that bind to these GABA receptors, you'll see barbiturate sites. So those types of drugs. Benzodiazepines also attached to it. All of these work together to increase the amount of inhibition. Another one that's of, especially given the change in our political climate in the past year, is tetrahydrocannabinol, also known as THC. And I do need to modify this slide a little bit because it's not just THC that's of profound interest. There's actually other cannabinoids that have been of particular interest, something that you might have heard of called CBD, cannabidiol. And specifically looking at this, you'll see that there is two types of receptors that are endogenous in the human body. We have two types of receptors called the CB1 and CB2 receptors. And we do produce our own endogenous cannabinoids called endocannabinoids. And they bind typically to the receptors. You'll see that CB2 is typically involved as a process for inflammation. You'll see CB1 receptors are typically not, we still have receptors for them, but they're not typically lit up. So here you'll see that the effect of extra types of cannabinoids, and we can get these from, obviously, marijuana. Okay. We have some of the active ingredients there are THC, which also bind to these types of receptors that enhance those responses. So THC typically is something that creates a psychoactive effect because we have these types of receptors, these CB1 receptors that are present in areas of the brain. And we have these types of receptors called CB2 receptors that are present in more the immune system side. So it's not uncommon that we're starting to find that these receptors, when with the intake of THC as well as CBD, will result in pain treatment, causing an increase in anti-inflammation. You'll see that other areas where we do have many of these receptors are also found in the hypothalamus, specifically the hunger center of the area. So take in excess THC that binds to these receptors and can trigger some of the symptoms that you would typically, such as increased hunger. You also reduce the satiety signals, the feeling of feeling full. That interrupts the signal between the hypothalamus and the GI tract. You'll see that these are also being heavily used in as an antiemetic. It also turns off the process of feeling nauseated. So typically people on chemotherapy that can't really take food in, they typically will end up feeling nauseated and throw things up. You'll typically see people that have chemotherapy that can't rely on other drugs that cause other side effects, will typically rely on medical cannabis for reducing nausea and increasing appetite. Multiple sclerosis also for anti-inflammation as well. So you'll see that this is a fairly heavy area of research, but again, because of the political climate behind these things, you have a drug, and I don't want to call it a drug, I mean specifically something that is naturally produced, something that we have endogenous cannabinoids on our own And we've got a lot of research that can be done with these things, but we also have a lot of shutdown of those particular research projects. And a lot of reasons sort of unknown, a lot of things that we can go into, but not really part of the whole physiology. So then the last thing I kind of want to leave with is the other neurotransmitters, and they can have mimicking effects. So you'll see that Parkinson's, when you look at Parkinson's, typically we have these constant contractions typically found in the extremities first. You see muscle stiffness, and typically with Parkinson's, you would find that dopamine levels are fairly low in those areas. So patients are given a derivative of dopamine called L-DOPA. So they'll be given L-DOPA to increase dopamine levels back to their normal levels. You'll see that you can block neurotransmitters or you can enhance them. Amphetamines increase dopamine and norepinephrine release, therefore driving not only the pleasure. When you look at methamphetamines can also increase those. So it increases the amount of pleasure that comes out of it, but also increases the amount of norepinephrine, catecholamines, things that increase the heart rate, increase the sympathetic drive. You'll take a look at some of the other, I talked about schizophrenia and other things that can end up removing the amount of neurotransmitters. Cocaine, for instance, blocks the transporters for dopamine reuptake. Same way that serotonin reuptake takes place, dopamine. Cocaine increases the amount of dopamine in those responses, and so forth. So that really concludes going in. This last